Dear all, welcome to the differential geometry class in Corona days. Last time I wrote down a theorem but didn't prove it. Let me restate the theorem and then we will prove the theorem. The first part of the theorem was this: if P is a point on the surface, is an umbilic point, which means that at the point P, all the normal curvatures are the same. It is constant in all directions. Then the shape operator S at P is just a scalar multiplication by the constant K, which is equal to K1 and K2. Since this is an umbilic point, P is an umbilic point, the principal curvatures are the same. And the second part of the theorem is this: if P is a non-umbilic point, meaning that the principal curvatures are different, then there are exactly two principal directions, and these principal directions are orthogonal. Moreover, furthermore, if E1 and E2 are these principal directions, vectors in these directions, then S E1 is just K1 times E1 and S E2 K2 times E2. In other words, K1 and K2 are just eigen values of the operator, and E1 and E2 are the eigenvectors, corresponding eigenvectors. Well, proof is just as follows. By the lemma, which states that the shape operator SP from the tangent space of the surface to itself is symmetric. Since this operator is symmetric, there are there is an orthonormal basis, let's say E1, E2, of the tangent space in which the matrix representation of SP is diagonal, right? Any symmetric operator is diagonalizable, and indeed you can find an orthonormal basis and it will be diagonalizable in that basis. So we have this. In this basis, the shape operator is diagonal, so it has this form for some real eigenvalues lambda 1, lambda 2. Okay. All right. Now, any unit vector u in TPM can be written as like this. Let's say C times E1 plus S times S2 for some C and S with C squared plus S squared equals 1. Well, this is because of the following. You see, I have the tangent space, let's say, and I have an orthonormal basis. Let's say this is the vector E1 and this is the basis vector E2. Let's say this is the unit circle. Now, any other vector, unit vector in the tangent space, let's say this vector u, can be written in this basis like this. And since E1, E2, and U are all unit vectors, C and S can be written like this. Actually, if I call this angle mu, then C is just cosine of mu and S is just sine of mu. And this explains the notation why this coefficient is called S and this coefficient is called S. Okay. All right. Okay, let's see. Well, then the principal curvature, the curvature, normal curvature, the normal curvature in the direction u is, which is just su times u, and this can be written as follows. So s of c of e1 plus s times e2 dot c1 e1, no, c e1 plus s e2. Here, of course, right, this is the matrix representation of SP in this basis. And this, of course, implies what? This implies that, sorry, oops. So let me write it this way. This is C times this, and this is S times S of ET because it's a linear operator. And uh, this is just lambda 1 times E1, and this is just lambda 2 times E2. Dot product CE1 plus SE2. And I know that E1 and E2 is orthonormal, is an orthonormal basis. So EI dot EJ is Kronecker delta ij, and therefore if you perform this multiplication, this is what you will get. Lambda 1 times c squared e1 dot e1, which is 1, and then I have lambda 2 times s squared e2 dot e2, which is 1, and then I have cross terms e1 dot e2, which is 0, and e2 dot e1, which is also 0. So this is what we get. Okay, well, without loss of generality, assume that lambda 1 is greater than lambda 2. These are real numbers because the operator is symmetric, therefore eigenvalues are real. So I have this. Okay, what was K1 and K2? K1 and K2 are the maximal and minimal values of this function, right? Ku. Well, Ku is equal to this, lambda 1 times c squared plus lambda 2 times s squared. S and c are just actually, if you want, this is just cosine squared mu plus lambda 2 times sine squared mu. And I assume that lambda 1 is larger than or equal to lambda 2. So I can just write this, lambda 1 minus lambda 2 times cosine squared mu plus I have lambda 2 times cosine squared mu plus lambda 2 times sine squared mu. Well, I can group this like this, and this is just in lambda 2 parentheses sine squared plus cosine squared, which is 1. So this is what we get. Lambda 2 plus lambda 1 minus lambda 2 times cosine squared mu. Okay. Well, this is a non-negative real number. Therefore, the maximal value of this expression will be obtained when this quantity is maximal. And this is maximal if cosine is 1. So, Ku, uh, uh, okay, let me write it this way. The maximum of Ku is obtained when cosine mu is plus minus 1. So it means uh, the angle mu is 0 or pi. Well, this means what? The angle is 0 or pi. So it means the vector u is either in the e1 direction or minus e1 direction. Hence, Ku becomes maximal if u is plus minus e1, and in that case, what is the maximal value? The maximal value is how much? So this is 1, therefore so k plus minus e1, it is just lambda 2 plus lambda 1 minus lambda 2 times 1, because cosine is plus minus 1, so its square is 1. So this is just lambda 1. But we know that the maximal value is K1. Therefore, lambda 1 is K1. So this implies K1 is just lambda 1. In other words, the principal curvature is nothing but the eigenvalue of the shape operator, the bigger eigenvalue of the shape operator. Similarly, this quantity becomes, it takes its minimal value when this is 0. Similarly, Ku, which is just lambda 2 plus lambda 1 minus lambda 2 times cosine squared mu, takes its minimal value if cosine mu is this time 0. In other words, when u is plus minus E2, right? Well, cosine is 0 means the angle is 90 degrees, so u is either in the E2 direction or minus E2 direction. Moreover, in this case, the minimal value is how much? So k plus minus E2. So this is just 0, lambda 2 plus lambda 1 minus lambda 2 times 0, which is lambda 2. Therefore, the minimal value, we know that it was K1. So K1 is equal to, no, minimal value was K2. I am sorry. K2. So K2 is lambda 2, or lambda 2 is K2. Okay. So the smaller eigenvalue of the shape operator is the principal curvature, the smaller principal curvature of the shape operator, or of the surface at the point P. Okay. Well, this actually covers also the case that where lambda 1 equals to lambda 2. Note that if lambda 1 is equal to lambda 2, then the shape operator in the basis is just this matrix lambda 1, lambda 2. They are the same. Therefore, the shape operator is nothing but lambda times u. And what is the minimal value and maximal value? Well, in this case, principal curvature is just SU times U. So it is just lambda U times U. This is just 1, so I get lambda. So it's a constant function. And this means K1 and K2 are the same, and they're both equal to lambda. Okay. So this finishes the proof. And we know that the principal directions E1 and E2 are orthogonal because the operator is symmetric. Therefore, the basis which makes the operator diagonal is orthogonal, right? We know that from linear algebra. We know that these two vectors are orthogonal to each other. All right, so we have proved our theorem. All right. Well, maybe as a summary of what we have done. Uh, so if E1, E2, K1, and K2, let's say these are as above, then for any unit vector u in the tangent space, we have, I can write this vector like this. So this is cosine nu times E1, sine nu times E2, and the uh, normal curvature along u is just su times u, and we just computed this, and it is just k1 times cosine squared nu plus k2 times sine squared nu. Okay, this is the summary. All right, now let's see Gaussian curvature. So this is the next topic, section 5.3, Gaussian curvature. Well, any 2 by 2 linear operator, in other words, a linear operator on a two-dimensional vector space, has two invariant numbers. One of them is the trace, the other one is the determinant, right? These are independent of the basis chosen. Therefore, for the shape operators, the determinant and trace are meaningful quantities, and we will give names to them. So let me just define those quantities. Let P be any point on a surface M in R3, and SP the shape operator, be the shape operator at the point P. The determinant of SP is called the Gaussian curvature of the surface M at P, and the trace of the operator SP is called trace, not the trace, but half of the trace, and the half of the trace of the shape operator SP is called the scalar curvature of M at P, and we have notation for this. Notation, Gaussian curvature is denoted by Kp. So this is just the determinant of Sp, and scalar curvature is just the trace of Sp, and it will be denoted by Hp. Well, the first lemma is this: if K1 and K2 are the principal directions, principal curvatures of M at the point P, then the Gaussian curvature is nothing but the product of these two, and the scalar curvature is just the arithmetic mean of the principal curvatures. And the proof is very simple, of course. Why is that? Well, we know that in the principal directions, the matrix representation was like this. So this was K1, 0, 0, K2, where beta is the orthonormal basis for the tangent space consisting of principal directions, where E1 and E2 are the uh, principal directions. Well, this means SP of E1 was K1 of E1, and SP of E2 is K2 of E2. Well, then, of course, what is determinant of the operator? Uh, Determinant of an operator is just the determinant of any matrix representation of that operator in a basis. So for this basis, the matrix representation is this. So Kp, the Gaussian curvature, which is just determinant of Sp, and this is just K1 times K2, and uh, scalar curvature, which is half the trace of the operator Sp. Well, this is just 1 over 2 K1 plus K2. Here, of course, we are using the following fact. Let me write as a remark. If you choose any other matrix representation, if beta prime is any other basis for the vector space at P, and let's say A is the matrix representation of SP in this basis, then of course we know this. A and let's say this matrix, okay, I know this. Then this is just some matrix P inverse, and then, okay, let me write it this way. Okay, K1, 0, 0, K1. This is just P inverse, and then A and P, where P is the base change matrix from which basis? From the basis, okay, so this is from beta to beta, so this should be from beta to beta prime, beta to beta prime, and then this is from beta prime to beta prime, and then beta prime to beta. Okay. The base change matrix. Okay. So in this case, hence, what is determinant of so k1 times k2, which is just this determinant. So this is determinant of P inverse AP, but determinant can be written like this. So this is determinant of P inverse, and then determinant of A and determinant of P. And we know that this 2 gives us 1, therefore this is just determinant of A. And this tells us that curvature, Gaussian curvature, can be determined using some other matrix representation of A. And similarly, the trace, so K1 and K2 is just trace of P inverse AP, right? Trace of this matrix, trace of this matrix is the trace of this matrix. But we know from linear algebra that trace of a product can be trace of A times B is the trace of B times A. So I can just replace the matrices like this, AP times P inverse, but this is just trace of A. Okay, so I just interchange this with this, and here P and P inverse cancels each other, and we get this. So what we see that as in the case of Gaussian curvatures, the scalar curvature can be computed by any matrix representation of the shape operator, not necessarily the matrix representation given in the basis consisting of the principal curvatures. Okay, so this finishes the proof. Okay, one other remark is this. On the, let's say, surface M, I have, let's say, normal field U, but then I have the normal field also minus U. So we wonder what happens if we replace this orientation with this orientation. We know that normal curvatures, changes, right? So the shape operators uh, okay, let me write this. Let uh, S P be the shape operator determined by the normal field U. Then we know that the shape operator for the field minus U is minus SP. Hence, replacing U with minus U replaces the principal curvatures K1 and K2 by minus K1 and minus K2. Thus, the Gaussian curvature which was K1 and K2, which is just equal to minus K1 and minus K2, is not altered. So this doesn't change if you change the orientation, but the scalar curvature, which was H 1 over 2 K1 K2 becomes, so if I change K1 and K2 with negative K1 and K2 becomes minus H, which is just minus 1 over 2 K1 plus, okay, I should say 1 over 2 minus K1 minus K2. So if you change the orientation, Gaussian curvature doesn't change, but the scalar curvature changes. All right. Okay. Let's see some examples. Let's consider a surface M given by an equation of this type. Z equals K1 times X squared, K2 times Y squared. Here K1 and K2 are just two real numbers. So this is a quadratic surface in R3. Well, let's see first the case K1 and K2 are both negative. So if you look at the cross sections, you see parabolas Z equals K1x squared and Z equals K2y squared. So this is a paraboloid like this. And if you look at, suppose you are at this point, P, and I have this direction, and we have also the other direction, let's say this one. Okay. So, yeah, maybe let me just, okay. So suppose this is the cross section Z equals K1 x squared, where y coordinate is 0. And let's say this is the cross section uh, Z equals K2y squared, x is 0. So two cross sections. if you compute the curvatures of this surface at this point, we will see that K1 and K2 are principal curvatures, and in this case they are both negative. We have done this computation, I guess, before, and we had computed principal curvatures. For the other case, let's say, okay, and in this case, let me say, what is Gaussian curvature, which is just K1 and K2, and it is positive, and this is just 1 over 2 K1 plus K2. So here, of course, maybe I should uh, point out that, this is the point. Let's say x and y are 0, therefore z is 0. Okay, so it is this point. For the quadratic surface, let's say z equals again k1 x squared plus k2 y squared, but this time let's say k1 is positive and k2 is negative. No, let's say, yeah, okay, doesn't matter. So we have a surface like this in this case, and our point P is here, again the point 0, 0, 0, and we have one direction like this. So this is the cross section, which is given by z equals k1 x squared and y is 0, and then we have the other section, all right, like this, and this is the cross section z equals k2 y squared and x is 0. And here in both cases, let me choose my normal vectors, uh, you know pointing upward. So this is my the u direction. Okay, so okay, and my point P. Okay, so P is 0, 0, 0, this point. All right. So again, this is my normal vector u. All right. So principal curvatures in this case, minus k1 and plus k2. Okay. No, principal curvatures. Yeah. Uh, no, no. This should be negative, and this is positive. Sorry. Yeah. Okay, okay. And what is the Gaussian curvature in this case, which was K1 and K2, but one of them is positive and the other one is negative, therefore this is negative. Okay. And for the third case, let's say K1 is 0 and K2 is negative. So I have Z equals, which was K1 x squared plus K2 y squared, but this is 0, so I have just K2 y squared. And we have what? We have a paraboloid like this. Okay, let me see. Okay, this is the surface. Let's say this is the point P, which is 0, 0, 0, and this is the cross section Z equals 0 and no, not Z equals 0, sorry. Yeah, Z equals 0 and Y is 0. So X is changing. And all right, the other cross section is this, and this is the cross section Z equals K2y squared and X is 0. Okay. And in this case, what is the Gaussian curvature? Gaussian curvature. One of the principal curvatures is positive, is 0, and the other one is negative. So this is just K1 and K2, and it is 0. Okay. All right. Now we have a technical lemma. Let me state and prove this. If V and W are linearly independent vectors, tangent vectors to M at P, so they are vectors in this vector space where M is a surface in R3, then we have the following identity. The shape operator evaluated on V is a vector, and if you take cross product of that vector with the shape operator at this vector, so here I have of course P, we get just the Gaussian curvature. This is the scalar times the vector this, and the other statement is this: SP times cross product with omega plus V cross product SP W. This is just 2 times the scalar curvature times V times W. And the proof is very simple. Okay. Now, these are linearly independent, V and W, therefore they form a basis. So let me just write it down. Since V and W are linearly independent, the set beta, which is V and W, is a basis for the tangent space. Let uh, A be the matrix representation of SP in the basis beta, where let's say A is this, A, C, B, D for some real numbers. Then, of course, what is SP of V? This is just A times V plus B times W, and SPW is just C times V plus D times W. And the rest is just, straightforward computation. Now, what is SPV cross SPW? Well, this is AV plus BW cross product CV plus DW. Well, V times V cross product is 0, W times W is 0, and A times W is minus B W times V. Therefore, we get this. A times D V cross W, and then B times C W cross V, but W cross V is just negative of this, therefore we have this. And what is this? This is nothing but determinant of this matrix. However, we know that the determinant of any matrix representation is nothing but the determinant of the operator, and that determinant is just the Gaussian curvature at P. Okay. Similarly, the other expression, which was SPV cross W plus V cross SPW this time, is what? So this is AV plus BW cross W plus V cross CV plus DW. Well, this is just, W cross W is 0, so the only non-zero term is this, A times V W, and then here V cross V is 0, so we have D times V cross W. So what we see is we have A plus D times V cross W, but this is nothing but trace of A times V cross W. Well, trace of A is just trace of the operator SP, and trace is just 2 times the scalar curvature. So this finishes the proof. Right, so we have proved the lemma. Let us see the lemma one more time. Sorry. Okay, a technical result. Okay, just a remark. You see, the principal curvatures satisfies this, so their product is H, and their sum is just 2 times K. Sorry, this is K and this is 2H. Therefore, K1 and K2, and hence K1 and K2 are the roots of the quadratic equation. lambda squared plus uh, okay, minus 2h lambda plus k, right? Hence, k1 and k2, the roots of this equation, what are the roots? So the coefficient minus of this coefficient, minus 2 minus h plus minus b squared, which is 4h squared minus 4 times this times this, so minus 4k divided by 2. So we get what? So we get h plus minus this 2 becomes 4 inside the square root, and we get just h squared minus k. Okay, we will finish this section by the following definition. A surface M in R3 is called flat if the Gaussian curvature is 0 for, sorry, if the curvature is 0 for all P in M, and is called minimal if the scalar curvature is 0 for all P in M. Okay, so any, for example, cylinder is flat, right? Because for a cylinder, one of the principal directions is 0. So, example, any cylinder is a flat surface. Actually, or a cone is a flat surface. Why is that? Well, you see, if you have a cylinder, it doesn't matter whether it's a circular cylinder or a parabolic cylinder like this. Okay. If you choose any point here, uh, there is a line going through this point. Therefore, along this direction, the the curvature, normal curvature is 0. Okay. And here also, you have this, so it contains a line. So the other curvature will be non-negative, sorry, non-zero, but one of them will be 0. So in both cases, uh, let's say k1 is 0, hence Gaussian curvature, which is k1 and k2, is 0. The other curvature will be negative or positive depending how you choose your orientation. And actually, why these are called normal is simple. You see, when you are given this surface, if you cut along a line like this, it becomes flat, right? Consider this, for example, flat piece of paper. So I make it a cylinder. I don't bend it. I don't, apply any force to, change the shape of it. Actually, uh, it was flat, and I just do it like this, and it is still flat. Also, if you put it like this, now it becomes a parabolic cylinder. It is still flat, okay? But if you choose a ball, for example, no piece of the ball can be flattened, okay? Uh, Unlike as piece of cylinder or cone. Maybe let me also draw cone like this. Of course, I have to remove the uh, tip of this. So like this. Here again, if you choose any point, then there is this direction and it contains a line. So in that direction, curvature will be 0, right? And therefore, K will be 0. Okay. And again, if you cut the surface along a line like this and open it up, you will get a piece of uh, you know plane. So when you cut it like this, you will get a piece of plane like this, and it is flat. Okay, so in this case K2 is negative, and here also K2 will be negative. If I choose my orientation like this, for example. Okay. All right. I guess yeah, this will be enough for today. Let's stop at this point, and I will see you next time.